Well, L'Hopital's rule is all about rational functions, one function divided by another, and also it needs to be of undetermined form. At first glance, this seems to be neither of those. Well, let's take a look. As x is going to negative infinity, x squared is going to go to positive infinity. And e to the negative infinity, well, let's see, e to the negative infinity, negative exponent means invert, so that would be 1 over e to the infinity, and that means 1 divided by infinity, which is going to be 0. So in other words, this one is going to infinity, and this one's going to 0. So we have 0 times infinity. So 0 times infinity, how much is that? Well, this is actually of indeterminate form because it depends on which one is going faster, which one dominates. If this one's going faster, as it goes off to infinity, it's going to dominate the whole problem, and you'll have the answer infinity. This one might dominate, or they might balance each other out, and you get the answer 42.7. So pretty much anything's possible at this point. But in order to use L'Hopital's rule, we need a fraction. Well, we actually got a fraction when we did this. A negative exponent means you've got a fraction. So I'm not going to do that with the negative infinity because that would just be a repeat of this, but do it with the variable. So we can use algebra to rewrite this one. The limit as x goes to infinity, the x squared will remain the numerator, sign. And then for e to the x, rewrite it as e to the negative x in the denominator. So essentially, having a negative would invert it back to the top, so it's the same thing, but just a different way to write it. So then this would become negative infinity squared, so that's positive infinity. And this would become e to the negative infinity, which means e to the positive infinity. So there it is. It's a rational function, and it's of indeterminate form, so we can use L'Hopital's rule. In other words, which one is going to its respective infinity faster? So the derivative on the top is just a 2x. The derivative of e to the negative x is e to the negative x, and then take the derivative of the negative x is a negative 1. And we would still have infinity, in fact negative infinity for that one, and negative infinity. So we need to do this one more time. And then hopefully you can see what's happening by using L'Hopital's rule. This is saying, hey, I'm so powerful, I'm an x squared. You take the derivative, well, I'm a linear function 2 to the x, I'm still going to infinity. And then it's just a constant function 2. It's sort of run out of gas. Well, the e to the x, like the Energizer Bunny, just keeps going and going and going. So when you take the derivative of this, it's going to be the e to the negative x, and then the negative from that's going to cancel the negative from that. There we go. And so now we have a 2 divided by e to the negative infinity. So 2 divided by positive infinity is 0. So in other words, this, yes, it's going to infinity, but this is going to infinity so much faster that it's basically like having a constant divided by infinity. And then a quick verification with the graph. Y equals x squared times e to the x. And then x is going to negative infinity, so I need to change this window. Let's say go to negative 100 to 0. And the y value is supposed to be 0, so negative 2 to 2 should be fine. So the graph has a little bit of action going over here, otherwise it's essentially a horizontal line. Let me change this to -1/2 and 1/2, and maybe this only needs to go out to 25. So it's got some curvature right there, but then it just drops down really close to 0. So you can trace it out to the left, and you can see the calculator actually thinks it is 0, but it's 0.0000, very close to 0. So in the limiting process, it becomes 0.